Hello! In our lessons, we are currently studying mechanics, and today we will be discussing various types of forces and how they relate to Newton's laws. We have learned that Newton's three laws describe how bodies behave based on the forces acting upon them. However, it is important to understand what forces can act on these bodies and what laws govern their behavior. Our task is to familiarize ourselves with the forces and apply Newton's laws to specific situations. Let's begin by exploring a force that is constantly present when we are on a planet like Earth: gravitational attraction. This force occurs between any two objects with mass and is known as the force of gravity. When we are on a surface, we feel the weight of our bodies due to the gravitational attraction between us and Earth. We can create a diagram of a free body on a horizontal surface to depict this force. In our lessons, we focus on mechanics and study different forces and their relationship with Newton's laws. These laws explain how bodies act depending on the forces acting on them. It is crucial to understand the forces at play, the governing laws, and their properties. Our current goal is to understand these forces and utilize Newton's laws in specific situations. Let's start by examining the force that is always present on a planet, particularly Earth: gravitational attraction. This force acts between any two objects with mass and is called gravity. When we are on a surface, we experience the weight of our body due to the gravitational pull between us and the Earth. To illustrate this force, we can create a diagram of a free body on a horizontal surface. And the body that's on it is subjected to several forces. What are these forces? The first force is the force we are talking about today, i.e. the weight of this object. And in this case, it is applied to the center of this body. This point is called the center of gravity. And it is always directed vertically downwards, let's say, to the center of the Earth, from the point of view of the fact that the Earth has a spherical shape. But why doesn't the body move in this case? Here, obviously, there is another force acting on the body which prevents the body from falling through the given surface, and the surface, when acted upon, will of course respond. This is where Newton's third law comes in, which speaks precisely of the interaction of two bodies. That is, there are bound to be two forces that begin to work against each other. That is, in this case, the given body will act on the surface itself, and another force begins to act on the body itself from the surface. This force is called the support reaction force. So actually, let's label them. So in this case, it's nothing more than the weight of this object and the force of the reaction of the support. These two forces, provided that the body is in a stationary state, will compensate each other. So the body is in equilibrium in this case. It will look like this. If the support is not moving, the two forces compensate each other, and in this case the same situation described by this equation will occur if the support is moving, but it is moving in a uniform straight line. Therefore, we can write down that this condition will be fulfilled if the velocity of this object we have 0, or the second option has its constant value. That is, suppose you are in an elevator that is moving uniformly vertically upward at a constant velocity. In this case, the force of gravity and the force of support reaction will balance each other, and for you it will seem that the elevator in this case is motionless, that is, you will feel yourself exactly the same as always. So, now the question arises further. How to calculate the force of gravity acting on this object? On what it depends? In this case, we can immediately say that here this force will depend on two factors. The first factor is the mass of this object. That is, the more massive the body, the greater the force acting on it. And the second factor is, of course, the properties of the planet itself. That is, how strong is the gravity on it and how strongly it will attract these objects. Therefore, we will take these two factors into account when calculating the force of attraction, and the formula will look as follows. Here, m is the mass of the given body, that is, the mass that will be responsible for how much the body is included in gravitational interactions. This is where we meet the second definition of mass in terms of gravitational properties. If we told you when we studied Newton's second law that mass here shows inert properties, i.e. shows how much the body responds to the impact on it and how much acceleration is obtained after the impact on this body, then here mass will already show itself from the point of view of gravitational characteristic of the body and already shows itself a little differently. We have talked about the fact that mass is not such a simple concept, and here we meet the second property of mass. And g is the acceleration of free fall, which we know for the Earth, and we will use this value in our tasks. This is the average value of the acceleration of free fall. That is, in different points of the Earth it may vary slightly. Again, it depends on how close we are to the center of the Earth, given that the Earth is not a spherical object, but has the shape of such an elongated ball a little bit, yes, from the poles. The g will be different at these points. Well, let's write gi and g2i, and respectively they are not equal to each other. To each other because the radius is polar, and the Earth's equatorial radius, they're different. Well, in this case, this vertical line is the conventional axis of rotation of the Earth. If the Earth had a perfect ball shape, then of course, in this case, the acceleration of free fall would be the same everywhere. So, in this case we have learned how to calculate the weight of an object that is on a fixed support. And in this case we see that it only requires knowledge of the mass and the free fall acceleration of a given planet. But what happens if the support itself starts moving too? That is, let us remember the same situation with an elevator and consider the case when the elevator starts moving, and it starts moving with acceleration. We meet such a case when we enter the elevator cabin, press the button and it starts moving. And it can move both up and down. It should also be taken into account in the calculation of the total weight of this object. Let's look at this situation. So, if we're in an elevator that starts moving with some acceleration vertically upwards, what will the object in that elevator? In this case, if we arrange the forces acting on the body itself, then naturally in this case there is still the force of gravity acting on this object and the force of reaction of support from the elevator itself. And if we write down Newton's second law for this situation, we know that the product of the mass of the body and the acceleration of the object is the sum of all the forces acting on that body. And now if we apply this vector equation taking into account the direction we choose, let's say y shows a positive direction, then the projection of these vectors on this axis will allow us to write the equation in scalar form. And it will look like this. From here we can find with what force the support acts on this object, i.e. we can find the force of reaction of the support. It will be the sum of gravity and this ma component. So instead of gravity, we'll put the value of gravity. If we take mass out of the bracket, we get the sum of two accelerations in the bracket. As a result, it turns out that this support reaction force is essentially an index of how this object acts on the support. We can denote this changed weight as WA, i.e. index A shows that the support itself moves with some acceleration, and we see that this value has become larger in comparison with the usual weight when the body is in a stationary state, and we can even say that we can describe it in this way, i.e. the value of ma plus the weight in the usual state. When considering the movement of the support, it can be observed that the indicator has the potential to vary. It is evident that if the acceleration of the elevator is directed downwards, the indicator will change its sign. Subsequently, the weight of the body will either increase or decrease. This gives rise to the concepts of overload or weightlessness, in which the weight of the body may no longer be present, resulting in no force being exerted on the support and a state of weightlessness. This particular circumstance is quite unique, and when tackling problems related to this scenario, it is imperative to determine the direction of the elevator's acceleration, and subsequently apply Newton's second law accordingly. This law establishes the relationship between the net force, the mass of the object, and the acceleration acting upon it. This is the end of this lesson. We will see you in the next lessons where we will apply this rule in practice. Goodbye.